Okay, this hour we will talk about a new topic, which is called clustering. Clustering algorithms are a little different from classification algorithms. Think about the data set, data like this. Okay, usually in classification model we have we can map our data. Okay, by using the features and map it to y, which is your output of your model, right? But for clustering, okay, there's no such target value. So for clustering algorithm, we don't have such kind of output. Rather, in clustering algorithm, we are trying to discuss the relationship between samples, not discuss the relationship between x and y, because we don't have y in clustering algorithm. Okay, so that is the basic concept of clustering. So usually we call it unsupervised learning, because we learn the relationship in those data by using their features. Okay, so here's the definition of clustering. So please take a look at this definition. We will introduce three different types of clustering algorithm. Okay, so first we take a look at the data. Okay, before we apply algorithms on your data, okay, there are some things you can do. First one is normalization and standardization. Okay, I believe you know what is z-score standardization and min-max and the mean normalization. But the reason we want to introduce right here is that before you apply any algorithm to your data, first you have to think about you can normalize the features, for example, using the new feature x1 prime. So the x1 prime might be normalized. Okay, so it should be something like this. So that is the z-score of the x1 data, right? So we use the z-score of x1 data as an x prime feature. So we don't use x1 anymore. There are several reasons we do so. The first one is for gradient descent we talk about. If you normalize all your data, okay? So here is an example right here. Here's the iris data set, right? We have four different features, okay? And as you can see that if you draw those values, okay, we have four features right here. You can see the distribution is a little bit different. Some values are smaller, some values are larger. But after we apply normalization, for example, you can use sklearn package, and there is a pre-processing scaled. This library can help you to scale your data to a normal distribution. Okay, so after you scale your data, the data will become this one. You can see that the four sets of data would become for example, the mean is 0 and the standard deviation will be 1. So the distribution of these four features will be closer. Okay, as we mentioned before in gradient descent, if you do so before you apply any algorithm, when you do gradient descent, it will be much easier for the gradient descent to quickly find the lowest MSE value with fewer steps. The reason why is the basin of the MSE, okay, it should be the theta 0, theta 1, that is MSE. Okay, it is much more easier for the gradient descent to find the lowest data point. It's right here, lowest data point of MSE value. MSE, it is a basin, right? It's a basin. If the range of different feature is quite different, okay, some ranges are smaller and some ranges are very, very large, and the Bayesian would become very strange. Okay, so that is one of the reasons we like to normalize data before using before apply your any algorithm. Okay, another reason right here is when we want to plot the data in a multi-dimension space. Okay, if you normalize the data would become someplace around the 0 point, right? If you normalize it. If you do not do so, the data might be somewhere far away from the 0 point, right? So after in this hour, we'll talk about some concept of distance and the clustering algorithm. It'll be much easier for some clustering algorithms or clustering algorithms to analyze data which has similar scale. Okay, so we strongly suggest that you perform data standardization or normalization before applying clustering algorithm. Okay, because most of the clustering algorithm needs to deal with some distance problem. So before you apply those algorithms, please do standardization or normalization. Okay, we will talk about later. So before we talk about the features, okay, here are several different scales. Okay, so please take some time to take a look at the definition of each scale, but we will go over it quickly. Okay, the first one is nominal scale. Okay, that is for x. Okay, the nominal scale means that if we encode certain feature by using numbers, okay, there are some encoding method which is not related to any we say they do not have any we say that for example that is black, that is red, that is green, that is blue. Originally, X1 is a categorical data, and it is color, right? But when we deal with such kind of data, we need to transform this column to values or numbers so that we can do some calculation by using X1, right? But when you do such kind of mapping, you can map black to 1, red to 2, and green to 3, and blue to 4, something like that. But basically, such kind of encoding, make no sense, because you can encode black to 10, red to 12, right? Green to 33. So if the data, okay, I mean the X1 is nominal scale, that means the number written right here, 10, 12, 33, and 4, you cannot use any other mathematic tools to add them together or subtract them or times or divide them, because such kind of number does not make sense, has no meaning. You cannot add them or subtract them. Those numbers are just represent they are different, they are in different categories. Okay, so basically we will not apply any features which is nominal scale by using, for example, linear regression, logistic regression, or any other classification or clustering algorithm on such kind of features. We will talk about how to deal with such kind of nominal scale features next week. Okay, so you have to be aware of such kind of feature. Next one is ordinal scale. Okay, that means, for example, ranking. First prize, second prize, third prize. of course, it has a number on it first, 1, 2, and 3, but it is very difficult for you to evaluate what is the difference between first price and second price, and what is the difference between second price and third price, because they might not be the same, right? So again, you can order them, but the difference might not be different between different rank order. Okay, so sometimes you can for example, you can, so that is a rank 1, 2, 3, 4, 5. Sometimes you can map this rank to a value by using a linear line or using an exponential line or any non-linear line. But you have to do it by yourself. Model doesn't do so. You have to make sure the line you choose right here is exactly what you want, so that you can map the rank data to numerical data, and that numerical data can use to be add together, subtract times, or division. Okay, so that is ordinary scale. You have to decide a function to map the order data to the to a real number. Okay, and the third one is called interval or distance scales. For example, Celsius degree. Okay, 1, 2, 3. Okay, and you can see that the difference between these degree are the same, right? The difference, right, between 1 and 2 Celsius degree and between 2 and 3 Celsius degree, they're the same, right? But there's one thing important, is that when we talk about 0 Celsius degree, 0 does not mean nothing. 0 is just a number between 1 degree and -1 degree, because that is temperature, how temperature works. 0 does not mean there's no temperature. Okay, 0 is just a number between 1 and -1. So that's what we call interval distance degree. You can add those degrees, but you cannot times. You cannot multiply those numbers, because 0 does not mean nothing. Okay, 0 is just a number. Okay, so next one is ratio scale. Ratio scale means centimeters, because the difference between 0 centimeters is that there are also the distance between 1 and 2 and 2 and 3 is still the same, right? But 0 centimeters, it means no height, no any height or width, right? So that is a little bit different when you describe temperature and your height or weight. 0 means really nothing. So that is called ratio scale. And for the ratio scale numbers, you can divide them, and you can multiplex them. Okay, so that is a little bit different. And for the absolute scale, that means, for example, probability or odds. We have talked about odds in logistic regression. They're just two numbers divided by each other. Okay, so before you before you apply algorithm, make sure you understand for every features. Okay, they belongs to nominal, ordinal, or interval ratio, or absolutely. Okay, because some numbers, we wish every numbers, it would be better if you use ratio scale features, because it makes sense to perform add, abstract, times, and divide, division, because 0 means 0. Okay, so take some time to think about your data and the definition of different scales. Okay, the next one I would like to introduce is distance. Okay, so because we don't have in our data set we don't have target y, right? So now we have to think about how do we compare different data point in the data set. The most straightforward is to plot all these data points in the multi-dimensional space. Okay, that is point 1, that is point 2, that's point n. So it is very straightforward. So we can use distance to evaluate the relationship between each data point. Okay, so for distance function, okay, there are two important properties. The first one is symmetry. Okay, that means the distance of point 1 and point 2 should be the same as the distance between point 2 and point 1, because for some scenario sometimes the distance function is asymmetric, but most of the time they are symmetric. Okay, and another one is the definition of distance and the similarity. Usually we will say that distance. Okay, if the range of distance is between 0.0 to 1.0, that the distance 0.0 means two data points, they are identical, right? So their distance is 0 because they're the same. The distance 1.0, that means these two data points are not similar, which say is very, very far away. Okay, the distance between this data point is quite large, so we say that the distance between this data point is 1.0. Okay, if you can normalize your data to between 0.0 and 1.0. Okay, so another concept is called similarity. Okay, so for two data point, if their distance is 0.0, and we will say that their similarity is 1.0. Right? If two data points, their distance is 1.0, which means they are far away, and we will say the similarity of these two data points are 0.0. So usually we will say that the similarity is defined as 1 minus distance. Okay, and of course at the first place you have to normalize your distance to 0.0 to 1.0. Okay, so that is the concept of distance. And how do we calculate distance? Because in this plan, okay, in this plan we have two data points right here, P1 and P2. It's very easy that we calculate the distance, right? So the distance is x1 minus x2 square, y1 minus y2 square, and root square. Right? So that is Euclidean distance. So you can simply write the distance function like this. Okay, it is the difference between x-axis. That is the difference between y-axis, and here's how you calculate the Euclidean distance, right? So here is another distance function. It's called Manhattan distance. That means if you walk along the x-axis and then walk along with the y-axis, so the length of the the length of the blue lines are Manhattan distance. So it's simply just add the distance right here. So of course you can write it in this way, okay? X1 minus X2 plus Y1 minus Y2. Here you put 1 right here, and you put 1 right here. So if you change it to 2, right, it becomes a Euclidean distance, right? So right here we can put it a p right here, and that will be the definition of Minkowski distance. You can use any number to replace p as the Minkowski distance. So you can think about one thing. You can define your own distance function. Okay, you can choose your distance function as long as it is symmetric. Okay, so the next one is what if we use a vector to present two data points A and B, right? So the distance, if we want to evaluate distance between two vectors, we simply just dot these two vectors. So that if you draw a line right here, so here's the projection of A and B vectors, right? So that's another way to evaluate two data points. Okay, if the projection is longer, that means A and B are similar. If the projection is 0, that means A and B vectors are orthogonal. Okay, so here is the definition, right? We have an A dot B vectors. So the definition is the length of A, the length of B, and the cosine theta. So if this number is larger, that means A and B are closer, right? So here is how we evaluate the similarity of A vector and B vector, which is called cosine similarity. So the definition is right here. If this number is larger, okay, the range of cosine theta is between -1 to 1, right? So if the cosine theta value of two vectors is close to 1.0, that means these two vectors are the same vector. So they are very similar. If the cosine value of two vectors close to -1, that means they have the opposite direction. So they are not close. They are not similar. So if they are 0, that means they are orthogonal. Right. So that is another way we use a vector, use dot product to help us to evaluate two vectors, how similar they are. So again, that is cosine similarity, right? So you can use this cosine similarity to calculate another value called cosine distance. Okay, you just simply use 1 to abstract the value of the similarity. Okay, so for Euclidean distance or cosine similarity, we have to calculate something on the plan, right? So they are numeric data. But what if some data looks like this? Okay, we have 3 data. Okay, Jack, Jim, and Mary, and their feature we can use F1. Okay, F1, F2, their feature are all categorical data. So there's a question that Jack and Jim are more similar, or Jack and Mary are more similar. Because they are not numbers, so we have to use another way to calculate the distance between these 3 data. Okay, so the way we calculate is like that. Okay, for data I and data J, okay, we simply just calculate this value. Okay, For example, we firstly map. Okay, for example, male is 0, male is 0, female is 1. True is 1, true is 1, true is 1. N is 0, Y is 1, N is 0. Positive is 1, negative is 0, negative is 0. No is 0, no 0, no 0. We first map the category data to 0 and 1. And then we calculate these 4 values. Okay, so A means the data I and is 0. For data J, they are both zeros. So think about this thing. To evaluate Jack and June, this one is 0, this one is 0. So we say, okay, A is 1, okay? This one is 1, this one is 1, okay? So we simply just A, B, C, D. It's very straightforward. Just simply calculate. Okay, that is 0, 0. So that means A, right? That is true. That is true. That's true. So that is 1 and 1. So that is B. That is no. That is N. That is Y. So that is 0. That is 1. So that is C. That's 1. That is 0. 1 and 0. So that is B. That's 0. That's 0. So that is A. So the final result is like this. Okay. So we put 0 right here. So the similarity of the distance of I and J is exactly, we have 5 different numbers right here. B plus C is 3. So the distance between Jack and June is 3 over 5. So that is how you calculate it. So basically, it just calculates how the number, the feature, how many features that this Jack and Jim, they both 0 or both 1. Okay, so so that is how you calculate this value, by how you calculate distance by using simply just count. Okay, so it's called simple matching coefficient. Okay, so that is the distance. And if you want to calculate the coefficient, that is the distance. If you want to calculate the similarity, you simply just, so that is the distance, right? So the similarity is 2 over 5. So that you can compare data points by using their categorical features. Okay, the next one is another thing which I think is important. That is called Jaccard similarity. So Jaccard similarity, the concept is from set. Okay, it's from set. Okay, think about, we have 3 different sets, and there are several different items in each set. And how do we calculate? The set A is similar to B, or A is similar to C. So the numbers right here is just an item. They are not numbers. They're just some items in that set. So to calculate the distance, to calculate the similarity, the similarity between set A and B, you simply just do so. That is the union, right? Set union, that is the intercept. Okay, let's take a look. How many items are A intercept with B? So that would be 3, 5, and 15, right? And how many items? 3, 5, 15, 8, 7, 9, 4, 2. Okay, so the answer would be 3. 2, 3, 4, 5, 6, 7, 8, 8. So the similarity of set A and set B is 3 over 8. So that is quite straightforward. And the distance is that 5 over 8. So simply just calculate how many items shared between set A and set B, right? Then you can calculate the Jacob similarity or Jacob distance. So there are several different ways to help us to evaluate the distance between data points. So after that, the next concept is called distance matrix. Okay, after we know how to calculate the distance value between two data points, then we will construct a matrix called distance matrix. So for example, we have 5 different data points right here. And the distance matrix looks like this, okay? At the diagonal line, okay, you simply just put 0 right here. Because the distance between A and A is 0, between B and B is 0, right? Because that is definition of distance, right? Okay. And then you simply just calculate one by one, okay? Distance between A and B, A and C, and D and E, and so on, so forth, so on, so forth. And as we mentioned before, because the distance function is symmetric, so basically distance AB and distance BA should be the same value. So basically you simply just need to calculate the value right here, and you just copy the value to the upper side. Okay, so that is the distance matrix. Some clustering algorithms require calculate the distance matrix first. Okay, so sometimes we need distance matrix. So here's an example that we have 5 data points, okay, and we have 3 different features. So basically we simply just use Euclidean distance, okay, and you can simply just use this package, okay, this library to calculate the distance right here. So basically, because we have 5 data points, so that the distance matrix would be 5 times 5, okay, and you can see that the diagonal value is 0, that because the distance between A and A is 0, okay. So and you can see that it is symmetric. So after that, you can obtain their distance matrix, okay. So we'd like to introduce 3 different clustering algorithms, okay, and you can use any distance function as you like, okay, to evaluate the distance between two data points, okay. You can use anyone, okay. The first algorithm we'd like to talk about is called k-means, okay. So that means, okay, given a set of data points, okay, so we have 2 features right here. So the k-means means, can you divide those data points into k different clusters? Okay, so we have an algorithm right here. So take a look. Okay, that is a step number 1. For example, if we would like to cluster those data points into 7 different clusters. Okay, so the first step of k-means is that you randomly, I think we have 150 data points in this plan. Okay, so the first thing is that you randomly choose 7 different data points among these 150 data points. Okay, I mark them right here. So that is step number 1. You simply just random choose them. Okay, randomly choose them. Okay. The next step of so let's we can use this one. Okay, the first step is to random select 7 of them. Okay, the second thing is that you calculate the distance value. Okay, we have 150 value, right? But 7 of them would be the red one, right? Would be the red ones. So now we have 143 data point, right? So we calculate, let's select one of them, okay? You simply just calculate the distance value between the rest of 143 data point, and you calculate the distance between the data point and these 7 data points you select, the red data points. There should be one red point which has the smallest distance with the data point you select right here, right? So you repeat this process among all the rest of the 143 43 data points. So now you have 143 sets of distance, and each set has 7 values. You simply just select the smallest one, okay? And for this data point right here, you choose a color, okay? And you can, for example, the color we choose right here is a dark brown right here, right? That means this data point, its closest red point is right here. So you can see that some data point, their smallest distance to this specific data point, okay? You color them using the same color, and we so on so forth can do so. In this way, you can partition all the 143 data point into 7 different clusters because you choose 7 different red points randomly at the first place. But that is just an initial process, okay? That is just an initial process. So after this process, you divide all 150 data points into 7 different area, although that is quite strange right here, okay? So the next step of k-means is that you remove, okay? So we say that you remove the red data points. You remove the red data points, okay? You just simply remove them, okay? Now you have 7 different areas, right? Then in each area, you select the central E of the central is calculated. For example, if we have 55 data point in this small area, okay, you simply just use, that's x1, that's x2. You simply just calculate the central E, which is the average of x1 and x2 in this small area. Then you can calculate central E. And those central E are, they are virtual central E. That means there's no actual data point at that central E. Okay? So you have new red points. And again, we remove all those colors and all those areas. Okay? And I have animation right here. Okay, so please execute your class node, and right here we can see that you can simply just execute all those we have to wait for a second, okay? Okay. So here we have data right here. So the X right here, that is the step, okay? So step 0, that means we simply just randomly select 7 different red points, okay? For the next step right here is we color all the rest of 143 data point by using the nearest red points, okay? So the color looks like this. And the next step is that we simply just remove all those red points. So we have 7 different regions. And then in each regions, we calculate the virtual central E of each small area. Okay, so now we have 7 new red points. Okay, and then we remove all the colors. And then we use this new 7 central E to color the rest of the 150 data. And then we remove the central E and we calculate the new central E again. And then we remove the color and divide the data by using the new central E's. And then remove central E, so on, so forth, so on, so forth. And as you can see that when you apply such process multiple steps, you can see that the central E now will be stable. That means the central E will not move dramatically again, That means the algorithm converges. Okay, so for after few steps, that is the result of k-means. We successfully divide the entire data set into 7 different regions. Okay, so that is how it works. Okay, so that is. So you can try this by yourself. Okay, so that is one of the good algorithm can help us to do such kind of clustering. But k-means has certain shortcomings. For example, before you apply this algorithm, you have to decide how many clusters you would like to have. In our example, we choose 7. You can choose 8, 4, 10, 11, which is okay. So it is a little bit difficult for us to know what exactly the case should be. So right here we have another explanation right here is that every time when you have more cluster, the number of cluster, okay, increase, okay, some value decrease, okay, what it is, okay. If we have some cluster data right here, okay, if you cluster this data point by using k-means, okay, with k equals 2, okay, the result will be a little strange, that the cluster might look like okay, the cluster may look like this, and then we have 2 central E. But as human being, you know, it makes nonsense because we know it looks like 3 clusters, not 2. So meanwhile, when you do such kind of clustering, you can always calculate the arrows and their variance. So the arrows is right here, right? You can simply calculate the distance in purple cluster, right? And you can see that there's some value, there's some data point which is far away from the central E, because we classify them into we cluster them into two clusters. Okay, so you can see that the distance within the class will be a little bit larger because some data point is far away. So that is what it means. The variance of the distance is large. But if you cluster the data into three clusters, the cluster will be maybe like this one, and the central E will be right here, and right here. And you can see that the distance within the class would be much smaller then you miscluster them into two clusters. The 3 would be the better number of cluster you should use. So sometimes you can see that when you cluster them with the wrong number of K, the average in cluster errors will be larger. But if you cluster them into correct K, this number would decrease dramatically. And of course, you can further cluster them into 4 different clusters. And I believe the cluster maybe looks like this. And as you can see, the distance, the average distance between central E and within between the data point within data point and the central will be again smaller, but it will not drop dramatically. So sometimes we draw this figure called elbow of K-means cluster. You simply just try different K values and observe the average within cluster distance, and you can see that if you cluster them, those data points, okay, with larger K, and this value drops. But if you observe there are certain elbow, okay, that's called elbow in this figure, then that might be indicate that is the correct, or that is the appropriate K value. So sometimes we choose this value or 4 or 5 somewhere near the elbow as our K value in K-means. Okay? So that is, and of course there are some other, the first shortcoming of K-means is that you have to decide which K you want to use, and most of the time we can draw the elbow curve and see which K is a more appropriate K value. And there are some other shortcomings of K-means. For example, that is the cluster value and the cluster data, right? And if there is an outlier right here, okay, and visually you can cluster them into 5 different clusters, right? But if there is a single outlier right here, if you choose K equals 5, and that will be 1, 2, 3, 4, 5. Because K-means is very sensitive to those outlier values, so our suggestion is that you can use more K. Okay, you can simply just use higher K to cluster your data, because some K will be distributed to those outliers. So even though you believe your data has only 5 different clusters, but we suggest you use 6 or 7 or 5, because there are always some outliers right here. So you have to give these outliers some K value. So usually they'll be larger 5, 6, 7, 8, or 9, even if you know your data has only 5 clusters. But there is always some outliers. So you need to waste some k value in those outliers. Okay, so that's one of the shortcoming of k-means. Okay, take a look at this discussion. Okay, so that is k-means. Okay, before we introduce next clustering algorithm, I would like to talk about another algorithm called KNN. You have to notice that KNN is a classification algorithm. It is under the category of supervised learning, which means it has Y. But the name of KNN and k-means that they both have K, so we introduce it right here. But the KNN is quite straightforward, so we will not explain too many mathematical things. We just show you some example. Okay, so for example, we have two features, x1 and x2, and there are two set of data, y equals 1 over y equals 0. Okay, the KNN means k nearest neighbors. So if you want to infer a new value right here, so that is a new data point right here, you want to predict its y is 1 or 0, you simply just use distance function to find the k nearest neighbors. For example, k now is 3, for example. Okay, so how do you do such kind of prediction? First, you calculate the distance of this new data point with all other data point in the data set, and you choose the 3 smallest distance data point. For example, one is right here, and the other is right here, and the other is right here. And as you can see that for 3 nearest the neighbor, 2 of them belongs to class 1, y equals 1. One of them belongs to class 0. So it's quite straightforward. For this new data point, its class, its prediction, the prediction of its class is 1. You simply just select, it's just like voting, okay? Just like voting. That is the basic concept of k-nearest. So basically, it is an algorithm, but it is very straightforward, okay? You simply just do so, okay? KN can be used for classification like this, and KNN can be also used for regression. Okay, that is how it works. Okay, for example, we have some data points right here. Okay, and we have a new data point right here. Okay, you simply use x1 and x2 value to calculate the distance between new value and this n training data. And again, you select k nearest data point. For example, we select 3, the nearest one. It's number 2 and number 15 and number 16. And when you do regression, you simply just average their y value, and you can obtain the y hat of this new data point. It is quite simple. You just average the y value, target value of your 3 nearest neighbors, and that's it. So it is a very simple, straightforward algorithm good for classification and good for regression. Okay. So we just want to talk about this quickly because it does not belong to cluster algorithm. Okay, it is classification algorithm. Okay, we will talk about hierarchical clustering next hour.